Okay. So we'll just graph it together now. So again, let's go. Let me start from scratch, like you guys are in Desmos. Well, yeah. Let me graph it with you guys. So let's go to Desmos. Okay. Oh boy. All right, here we go. So again, we're going to graph the normal distribution. I want you to graph has mean 12 and standard deviation 0.3. So you could use the keyboard as I'm doing here. You click on it. Okay. You go to functions, like so. Then you click on normal, DIST, normal dist. And you want to type the standard, you want to type the mean is 12. Let me do this. I clicked, okay, yeah, 12, comma, 0.3. Okay, we don't see it here, so we may have to click and drag like this. There it is. I'm going to zoom in as well. See? So this is the graph we get. Okay, so this is the graph we get. You can also, oh, okay, let me go back a bit. I think there's a, yeah, okay. So let's go back a bit. So we're here. Okay. So again, that's the graph. In the notes, I think the color I have is red, but again, that doesn't make a difference, I think. So we have that. Okay, so that's the graph we get. Okay, well, let's now, okay, so that's what we get. I just wanted everyone to have practice graphing this. So I really hope everyone tried. Let's now go back to the notes. I know I'm bouncing back and forth between the notes like this, but, you know, it's important. I don't think there's a way to share two things at once in Blackboard. At least I don't think there is, but I could be wrong about that. Anyway, let's now, so again, this is here. This is the slide we were on. So the next slide here. You know, the color's different, but that doesn't matter, as you can see. All right. Okay, so now we have another example I wanted everyone to try. Although I did this with the other class, let me do it with you guys as well. What I wanted everyone to do was to graph, here, let's read the problem, sorry. Well, you're going to sketch a graph in Desmos and you fill in the blanks here. Okay. But let's do it together because I did it with the other class as well. So gear circumference, we're told that gear circumference for a manufactured bicycle part, okay? We're told that the circumference is normally distributed with the mean of 4 inches and the standard deviation is 0.2 inches. I think this is actually from the book. Yeah, this is from the book, but the numbers I changed a bit. So not only are we going to sketch the graph using Desmos, we're also, okay, going to fill in the blanks here, just like the previous example with the empirical rule. So again, gear circumference for a manufactured bicycle part, it's normally distributed. We're told that with a mean of 4 inches and standard deviation of 0.2. Okay. So by the empirical rule, we have that 68% of the data values, or in the context of the problem, 68% of the gears, 68% of the gears had a circumference between 4 minus 0.2, again, that's the mean minus the standard deviation. So 68% of the data values, okay? Or in the context of the problem, 68% of the gear circumference values is between 4 minus 0.2 which is 3.8 inches, and 4 plus 0.2, 4.2 inches. Right? The mean is 4. The standard deviation is 0.2. Right? So 68% of the gear circumference lies between, excuse me, let me say it again. 68% of the bicycle parts have gear circumference between 3.8 inches and 4.2 inches. Now, 95% of the bicycle parts have gear circumference between 4 minus 2 times 0.2, which is 3.6 inches, 4 minus 2 times the standard deviation, okay? 4 minus 2 times the standard deviation. Here we have 4 plus 2 times the standard deviation, right? We're adding 2 times the standard deviation to the mean and subtracting. So we have 4 minus 2 times 0.2, which is 3.6. We have 4 plus 2 times 0.2, which is 4.4 inches. So it's just the empirical rule is what we're using. Here we have 99.7%, right, of the parts have gear circumference. Okay, I think the sentence I might have is not 100% correct, but hopefully everyone gets the right idea. When I post the notes, I'll fix it. 4 minus 3 times 0.2, which is 3.4 inches. 4 plus 3 times 0.2, which is 4.6 inches. So again, the idea is the empirical rule. You're subtracting from the mean 3 times the standard deviation, and you're adding 3 times the standard deviation. That's what we're doing. That's what we're doing. Okay? That's all we're doing. So even though we don't have the data listed in front of us, we can still, figure out between what data values do most of the data, between what numbers most of the data values lie. Okay. And this is the graph. The graph here, again, the mean is 4, and the standard deviation we're told is 0.2. So that's what I'm doing. I'm graphing it, as you can see. All right. So are there any questions on this example? I hope I didn't mess up the explanation. The whole idea here is just the empirical rule. That's all we're using. Okay. All right, let's keep going then. So, we kind of saw from Desmos, actually, and also from last time, that for any number b and any positive number a, you can consider a normal distribution whose mean is b and whose standard deviation is a, for a positive number b and standard deviation and positive number a. For any number b and positive number a, we can consider a normal distribution whose mean is b and standard deviation is a. But there's a special case that people like to consider, and the special case is when the mean is 0, the standard deviation is 1. We have what's called then the standard normal distribution. That's what we have then, the standard normal distribution. And now this is actually the most important. That this is the one that people generally deal with. Okay? All right. And how do people generally deal with that the most? They use the idea of standard scores, also called z-scores. Basically for that, it's the number of standard deviations a specified data value is from the mean. So let me say that again. A standard score, a z-score, that's the number of standard deviations a specified data value is from the mean of the distribution. Standard scores are generally abbreviated by that letter z. So basically what people do, especially with normal distributions, they'll take a data value and using this formula here, they'll convert that data value to a z-score. That is, they'll find a z-score for that data value. And then they'll analyze the z-score. They'll see what number it is they'll see what number it is, which tells you, as we'll see here, how far away from the mean that data value is, how many standard deviations away it is. And there's other stuff we'll see later on that the z-score can tell us. So again, with normal distributions, what people do is they'll take a data value and find the corresponding z-score. And then they'll analyze the z-score somehow. They'll see, okay, well, how many standard deviations away is it from the mean? They will also consider, as we'll see later on, percentage of data values, that kind of thing. We'll see that later on, though. Later on Thursday, I think. They'll do a lot of things like that. I mean, with something like Desmos, there might be less of a need to work with z-scores. It's still important, though. You don't want to rely everything on technology, so to say. Sometimes technology, can fail you, right? It doesn't always work the way you want it to. So it's good to know how to work with things like the standard score and the z-score, even though we have Desmos.